In this section, we will examine applications in which we need to find the maximum or minimum values of a function. For example, a physical or geometric quantity is often described by means of some formula Q equals f of x, where f is a function. Thus, Q might represent a temperature, current of an electrical circuit, or volume of a gas in a spherical balloon. Of course, we often use other symbols, such as T for temperature, a lowercase t for time, R for resistance, V for volume, etc. In application, these help find the maximum or minimum values of Q. They are sometimes called optimal values because they are, in a sense, the best or most favorable values for the quantity Q. The task of finding these values is called an optimization problem. The guidelines for solving an optimization problem are as follows. First, you must read the problem carefully several times and think about the given facts as well as the unknown quantities that are to be found. If possible, sketch a picture and label it appropriately, introducing variables for unknown quantities. Words such as what, find, how much, how far, or when should alert you to the unknown quantities. Then, write down known facts together with any relationships involving variables. Determine which variable is to be maximized or minimized and express it in terms of one of the other variables. Find the critical numbers of the function obtained in this guideline, and then determine the extrema using the first or second derivative test. For example, an open box with a rectangular base is to be constructed from a rectangular piece of cardboard 16 inches wide and 21 inches long by cutting a square from each corner and then bending up the resulting sides. Find the size of the corner square that will result in producing a box with the largest possible volume. So, first we must take into account that the rectangular piece of cardboard already is 16 inches wide and 21 inches long. These little squares are x. So this is our sketch and these are our variables. To decide the volume, we see that this length is going to be 21 minus 2x, because there's an x here being cut off and an x here. Likewise, this length is going to be 16 minus 2x. Now, the quantity to be maximized is the volume of the box, V. Referring to the figure, we express V as a function of x. Volume equals x times 16 minus 2x times 21 minus 2x. Simply length times width times height. Also, since 2x is greater than 0 but less than 16, the domain of our function v, when we divide by 2, is between 0 and 8. Going back to this, we know that to find the critical numbers for the function, we must differentiate v with respect to x. We now can find that our critical numbers are here 28/3 and here 3. However, we know that 28/3 is out of the domain of the function. Therefore, 3 is our critical value. Now that we have x equals 3, we must check it. The endpoints 0 and 8 of the domain yield the minimum values 0. For the critical number 3, we obtain that the volume is 450 units cubed, which is the maximum value. Consequently, a 3-inch square should be cut from each corner of the cardboard in order to maximize the volume of the resulting box. Here's another example. A circular cylindrical metal container open at the top is to have a capacity of 24 pi inches cubed. The cost of material used for the bottom of the container is 15 cents per inch squared, and that of the material used for the curved part is 5 cents per inch squared. If there is no waste, find the dimensions that will minimize the cost of the material. First, we begin by sketching a typical container, as I've done here, letting R denote the radius and H denote the altitude. Then, we write down what we were given. So, we know that the volume is going to be 24 pi inches cubed. And the cost for the bottom is 15 cents, and the cost for the top is 5 cents. The quantity we wish to measure is the cost C of the material. Since the cost per square inch for the base and the curved part are respectively different, we have, in terms of cents, the cost of the container is 15 times the area of the base, which is pi r squared, plus 5 times the area of the curved part, which is 2 pi r h. We can simplify this to find that the cost is 5 pi times 3 r squared plus 2 r h. We can express c as a function of one variable r by expressing h in terms of r. Since the volume of the container is 24 pi inches cubed, we see that pi r squared h equals 24 pi, or h 24 pi, or pi r squared h is 24 pi, or h equals 24 over r squared, as the pi's cancel. Now, we substitute, getting 5 pi times 3r squared plus 48 over r as the cost. The domain of the cost is 0 to infinity. Next, we find the critical numbers by differentiating with respect to r. We end up getting 30 pi times r cubed minus 8 over r squared. Since dc dr equals 0 when r equals 2, and we see that 2 is the only critical number. Since dc dr is less than 0 if r is less than 2, and dc dr is greater than 0 if r is greater than 2, it follows from the first derivative test that c has its minimum value if the radius of the cylinder is 2 inches. Therefore, the corresponding value for the altitude is 6 inches.